Okay, here we go. All right, and now we also filled the 2 minutes that I announced with our mumbling. So I guess we can start, and I first hand over to Kurt.
Right. Welcome, everyone. This is our second ClimTip webinar. Today, we will be looking at math analysis application to study the tipping, early warning signals of tipping of the AMOC, the Atlantic overturning circulation. And before we continue with the talk, I just wanted to say that we have launched a next version of our website, ClimTip website. It's online and should be fully functional. So go ahead and visit. We will be publishing news articles, any updates on publications there. And the next ClimTip seminars we're planning, I just wanted to give a shout out to the next speaker, who will be hopefully Imke Hopp, and we will be talking about communicating climate science. But today we have Christian Kuehn from TUM, and I'll let Nicholas introduce him.
Yeah, thank you, Kurt. I'm really happy to have Christian as a speaker today. We've actually had quite some collaborations ongoing also since 2018, when we started writing the proposal for the sort of predecessor of ClimTip, which was TIPES, where Christian was also already leading the sort of the work package that made sure that everything also made sense mathematically. Let's put it that way, to sort of keep our feet on the ground a little bit. And that's continuing into ClimTip, and where Christian now focuses on, together with Andreas, will focus on resilience concepts, and of course, based on that, early warnings for higher dimensional systems. And I guess what we will hear today is sort of the mathematical foundations of that, which I'm always very much enjoying to hear. So Christian studied math at Jacobs University Bremen and University of Cambridge, received his PhD from Cornell in 2010 already, and then joined TUM as a professor in 2016. And he works on, let's say, a combination of differential equations, stochastic differential equations, dynamical systems, multi-scale systems. So yeah, a lot of a very wide range of expertise, which I think we as climate scientists, I mean, that's the kinds of brains that we need to pick. Yeah, maybe just to complete this, Christian has also won some very significant prizes, including a Lichtenberg professorship by the Volkswagen Foundation, as well as the Richard von Mises Prize. And with that, floor is yours, Christian. Very much looking forward to this.
Thanks very much, Niklas. Thanks for the very nice introduction. I hope you can all hear me and see my cursor. I think that's sort of important. So what I will do today is I will give a little bit of a tour, so to say, starting with something that you definitely all know from climate science and the AMOC, meaning a motivation why we would need early warning signs. I will keep that quite brief. Then I will go through quite a bit of the theory, how this theory has developed more or less already since, well, I would say 10, 15 years, and where we are currently with the theory. And then in the end, I will come back to a concrete application. So it will be a little bit of a tour, sort of from the starting point back to the application in the end. Okay, so introduction is pretty clear. I mean, there are many systems, many complex systems that could tip. The AMOC, so the Atlantic Meridional Overturning Circulation, basic salt advection feedback, or you could even call it the heat pump from the sort of tropics or equatorial sort of areas up to the north. That's basically part of what it does, not everything, but part of what it does. And it's one of the many climate tipping elements that at some point people, might sort of cease to actually provide the current state, the current stable state of the sort of oscillation that's currently present in the MOC. And the question is, okay, is this even sort of physically plausible that this system shuts off, that there's an ocean stream in the North Atlantic to the tropics and back that at some point can shut down? Yeah, is this reasonable? And this can happen. So there is certainly many observations that this is by no means a sort of constant object that for all times does always the same thing. So there are many events that have been recorded from ice cores. Here's just an ice core record that many of you have seen of an isotope where you can basically figure out how strong the AMOG was back in time. And you see that indeed it can happen that this system, this ocean system, has sort of wildly alternating states. And the question would be, can you somehow, from the current modeling, from the current analysis that we have available, can you write a model? Can you predict what the AMOG is going to do? And can you incorporate data to make maybe even accurate predictions on what it's going to do in the future? Of course, this is really, really difficult. It's a really difficult problem. And the main takeaway message that everybody in the climate community sort of agrees is that it is a highly complex system. It's certainly spatial. It operates on many time scales. There are many sort of stochastic effects, either stochastic forcing that it gets from other systems or from fluctuations that are inherent in the system, so finite size fluctuations. Or it could even sort of be stochastic in the sense that the parameters are random. I'm not going to talk about this today, but it's clearly another important aspect of randomness. So it's a highly complex system. We also agree that it's a highly difficult system to manipulate experimentally. You cannot just sort of say, okay, let's change the ocean completely. Let's try a little bit what the ocean is going to do. And then let's change it again back. That's clearly not what's going to happen. And there are critical transitions or tipping points, whatever terminology you prefer. So transitions that are drastic, sudden, and rapid, that somehow means that this system can change if you move a parameter or if you let it run in time and there's a feedback loop that moves it to another alternating state. And usually what you need to do in these systems, not only the MOG, is to consider low-dimensional observables, because clearly you cannot measure everything over time all the time about the system, because it's just too much. So you cannot measure the flow of the ocean at every position in the ocean all the time. This would be far too much to ask. Yeah. So there are similar scenarios, let me just point out, in many other areas of science. This is not only climate systems where this happens. So you have the same situation in ecosystems, the same situation in epidemic spreading, the same situation in political and social interaction networks, the same situations in complex medical conditions that are systemic for your whole body. It's very difficult to somehow experimentally purely probe that system. So what you need is good modeling, and you need a good understanding from a modeling perspective of how this system behaves and when and if you can predict certain transitions in the system. So this sparked sort of a level of interest. I can only cite a few papers. There are many, of course, that sort of deal with this area. So I will give sort of pointers to the literature in gray here and there. So the basic challenge is, first, suppose you have a time series. Let me go a little bit more quantitative. And you have an observable, say U, and there's another time series in B, also a time T and observable U. And you see somehow it's already a debate, of course, where you put the red dashed vertical line. At some point, this time series seems to behave quite differently. Yeah. So there seems to be some sort of point where after that, it really behaves quite differently. Yeah. And the question is, can you define what the mechanism of these sort of drastic changes in these observables is? And if there are warning signs, so you can think, can I sort of compute from the left side of this vertical red dashed line, whether there is this drastic jump on the right side of the dashed vertical line? And even if you can sort of find warning signs, mathematically, you have to quantify precisely when they somehow work and when they actually do not work. So you have to look at the assumptions of this theory. And there are dynamical mechanisms and scaling laws that should hopefully be universal, in the hope that you don't only do it once for every sort of type of transition that you see in a particular model, but you're hoping to transfer the insights to other models naturally as well. So there should be a generic theory. And from a mathematician's perspective, you could also ask, well, what techniques for analysis do you use? And also from a data science perspective, you could sort of ask, what should we actually measure and where should we measure our observables? Yeah? Because there's a choice usually, right? Think about the ocean. I could measure the ocean at many different places over many different time scales, but what should I really measure to best predict what the ocean's going to do? It's not very easy as a problem. So classically, the first thing you think of when you think of critical transitions would be classical bifurcation theory, or in statistical physics, the theory of phase transitions, yeah, whatever you like to call this. And here's just the very simplest kindergarten version of undergraduate mathematics. So you have a differential equation like in ODE, u prime is equal to f of u. V in this case will just be parameters for now, and you move the parameter and you see, for example, here in this so-called bifurcation diagram, that if you move V on this horizontal axis, that you have one stable state, this is the sticker gray line, and one unstable state, the dashed gray line. These sort of states of this ODE, in this case, at some point collide and in the end disappear, or basically they move into the complex plane. So you don't see them in real space anymore. Oh, there's an arrow wrong. I should fix the arrow. This arrow should point downwards. Okay, so this arrow is pointing downwards. I should fix this. And you see that this is a saddle node bifurcation where you have an unstable state that collides with a stable one, and afterwards you have no state. That's anymore no steady state. So definitely you will have a jump if you go over this. In this case, the jump will be actually downwards. The same could happen at a transcritical bifurcation where two branches of equilibria cross. They exchange their stability, here in this case at 0, 0. And if you think about, for example, getting attracted first to this state to 0, then you move your parameter, say, and at some point, you're over this point. It could happen that by some perturbation you land in the upper half plane here, and then you would be sort of repelled from this unstable state, and you would jump to a faraway state. And that's sort of very well understood how to unfold and understand bifurcations. Very classical work from the 70s and 80s, and the higher dimensional bifurcations, say in the 90s, global bifurcations also early 2000s. And this is sort of well documented in many books. Now, you could think that this is a basic building block, and indeed it turns out that effectively bifurcation theory describes many of these tipping points or critical transitions as a background mechanism, whether it's autonomous or non-autonomous bifurcation theory, it's still bifurcation theory. And okay, there's also the case when you have large noise that sort of randomly kicks you somewhere. I will not talk about this case today, but in some sense, that's another matter, which basically means that you haven't really modeled the sort of noisy scales to an amount of detail where you understand what is the mechanism that randomly kicks you. I will basically focus on deterministic plus small noise today. So you also need parameter drift, and to include parameter drift, the easiest way is to go to multi-scale systems. So you say, I have my normal, say fold, and now I want to also include the fact that my parameter is moving. I can do that by adding a slow drift to this parameter V, and then if I start at an initial condition here, I first get rapidly attracted to this upper stable branch. I slowly drift along it because V is increasing, and at some point I fall off this bifurcation point. And indeed, if you look at the time series of U, this looks a little bit like these observables that we have seen in the beginning in this sort of motivating question. And I will call the set of equilibria for this fast-slow system if you set the fast equation equal to 0, I will call this the critical manifold. So you set the first equation equal to 0. In this case, the F would be minus V minus U squared. This would be the critical manifold, and this critical manifold I will call normally hyperbolic if I linearize with respect to U. So you have 2U, and if there's this 2U in more generality has no spectrum on the imaginary axis, in this case it's just a 1-by-1 matrix. It only has spectrum on the imaginary axis when U is equal to 0. Then I will say if it has no spectrum on the imaginary axis for this linearization, this critical manifold is normally hyperbolic. And if there is spectrum on the imaginary axis, in this case at 0, 0, then it's not normally hyperbolic, which is expected. It's a little bit like in bifurcation theory, you know that you're basically breaking hyperbolicity, and that's where the bifurcation is coming. And okay, so this is the basic sort of setup. And let me highlight that you can also generalize this. So you cannot only sort of do this in one dimension and make a slow parameter drift, but you could also do this for general fast-slow systems where you basically have a system that is just n fast variables and m slow variables. And you can rescale that system to write it on different time scales. On the left, it would be on the fast time scale. On the right, it would be on the slow time scale, because on the left, it's in t, and if you scale t with epsilon, you get a slow time scale. For epsilon positive, these systems are equivalent, but for epsilon equal to 0, they are non-equivalent. And that's usually the mathematical sort of building block. You analyze on the fast and the slow time scales the limits as epsilon tends to 0, and then you're trying to build together what's going on. If you go to the previous picture, if you set epsilon here to 0, then this means V is not doing anything. So V is a parameter. We know we just get attracted to the stable state here. But if we are near the stable state, then basically this first equation is not moving anymore. So we should change to the other time scale. So if we change to the slow time scale, we move the epsilon over here, which means we constrain ourselves to the critical manifold when this epsilon is equal to 0. And then we slowly drift along this manifold, which is indeed happening here. And then you see this sort of singular decomposition, meaning analyzing just the fast and the slow limits of the system, that reaches sort of its limits here, where near this so-called dynamic fold, or near this fold in a fast-slow system, you see that the fast and the slow variables interact. And that's why these points where you lose normal hyperbolicity are much more complex than the points, in some sense, that you see up here and over here. Yeah, the ones that are normally hyperbolic. Good. And there's lots of theory. I will not go through this. There's many ways to analyze fast-slow systems: asymptotic analysis, non-standard analysis. Geometric perturbation theory is more what I'm familiar with and basically used most of the time. But there are many interfaces of all these areas for fast-slow systems. I've written a book in 2015, which is quite long, so a couple hundred pages, where you can actually look at all the interfaces, how to analyze such deterministic fast-slow systems. But for today, it's okay if you keep such a picture in mind. Yeah, that's perfectly fine. Okay. So now we also know that in the first pictures of the time, we have seen that there are stochastic perturbations to the system. So let's suppose we are forcing our system, for simplicity today, with additive noise. It could be more complicated noise. Most of the things still work, because if the noise is generic, this would mean you sort of to lowest order, you have an additive contribution, then it would still be fine for all the theorems that I'm going to prove. So it's not really a big limitation. So suppose I have a stochastic fast-slow normal form where you again get attracted to the upper branch of the critical manifold. Then you fluctuate around here a little bit, and then at some point you jump at this fold. If you do that, well, on the left, I've written it in the physics notation. On the right, I've written this in the sort of E2 stochastic differential equation notation. You notice that it's actually mathematically quite a tricky problem now, because you have small noise, you have this slow drift, and you also sort of have to understand that you're near a point where you lose stability. So you basically have three small quantities. And for today, I will always assume that the noise is so small that the drift is winning, meaning that if I have such a trajectory with high probability, I get to the fold point and then I jump. Whereas, of course, you could assume if the noise is large, you might jump before you reach the fold. So I assume the regime that you can technically work out for every bifurcation. In this case, for the fold, you can work out you need sigma much smaller than square root of epsilon. If you have that asymptotically as sigma and epsilon tend to 0, if this is asymptotically correct, then you can assume that the noise is sufficiently small, meaning that you get to the fold before you jump over the unstable branch. Okay? So there are small quantities, and the problem is doubly singular. But also you see that this is sort of the base of early warning signs. If you somehow look at this trajectory over here, you just cut out the red bit and you plot the variance of the red bit, then you see that the variance already sort of in the eyeball metric of this single trajectory seems to increase if you move closer and closer to the fold. And this is indeed understandable by sort of easy argument that they're slowing down, meaning that the critical manifold is normally hyperbolic and attracting at the top. And the rate of attraction is given by linearizing. So the rate is minus 2u. But if you move locally this local linear rate and you move u to 0, then you see that this rate is diminishing. If the noise is additive and fluctuating, then this means that the noise will sort of relative to the deterministic term, the drift term, so to say, increase in relevance, meaning that the fluctuations go up, which entails that indeed there's a warning sign that's given by increasing the variance. So far, so classical. Okay, the rough historical context, I cannot give everything here because then I would need to talk for like 10 hours. But roughly speaking, bifurcation theory really in its more modern form started to evolve in the 1940s, together with phase transition theory and statistical physics. Then this critical slowing down and scaling law business started in the 1950s, actually. So roughly at the end of the 1950s, early 1960s, it was known that there's critical slowing down. So this is not an invention of recent years. The idea to use it as warning signs and to combine this with bifurcation theory at the latest was already quite good, established in the 1980s. So there are nice papers by Wiesenfeld, for example, in the 80s that do this. In the 1990s, people also looked at non-autonomous bifurcation theory for systems that are time-dependent. So basically, you could also do many bifurcation theoretic concepts for non-autonomous systems. Then also in the 1990s, in parallel, people started looking at stochastic bifurcation theory. Then in the 2000s, there was a wave of sort of popularization, particularly in ecology, of using these early warning signs. And then in the 2010s, we sort of started in mathematically pinpointing a generic theory to make it applicable to a wide array of systems. That's very rough, of course. So you need thousands of citations for this. Hundreds of thousands potentially to make this accurate. But I thought, okay, I will put in a historical nugget from that I had with a nice conversation with somebody who's quite famous in the math community, who worked on stochastic dynamical systems a lot in the 80s and 90s. Ludwig Arnold, who was a professor in Bremen, now long retired already for more than 20 years. But I emailed with him, I still have his mail, because Ludwig Arnold was in Bremen, and as you as climate scientists know, Klaus Hasselmann was for a long time in Hamburg. And you know Hasselmann probably, or at least hopefully, most of you do, if you're in the climate community, who won the Nobel Prize for climate science a couple of years back. But since Bremen and Hamburg are so close, I thought I would ask Ludwig Arnold whether there was any interaction between math and climate science, because they were both pretty close. And I got this very nice reply from Ludwig Arnold. I cut out all the personal bits and hello and so on. So I left it in German because I think it's sort of charming in German, and I couldn't dare to translate this charming German professor sort of letter into English. So basically what Arnold last year or 2 years ago, actually from his notes, he had notes of everything. So he was a very dedicated German math professor, sort of I very much sympathize with this. So he had notes, and he looked at his notes, and he found that the first time he talked to Hasselmann was apparently in November of 1991 at a colloquium at the University of Bremen. And Hasselmann talked about general circulation models at this colloquium. And in the Nachsitzung, so this is the dinner afterwards, he sat next to Hasselmann, and he asked him whether stochastics is relevant in climate models, because Arnold was working in stochastics. And then Hasselmann said, yes, of course. And he gave the sort of Hasselmann program work, the 1976 famous Hasselmann paper, to Arnold. And Arnold said, oh, well, that's nice. So he took a note of it and put it in a sort of folder that said to do. And as a mathematician, if it's once in that folder, you don't give up, you work on it until it's done. And I very much sympathize with this. So many years later, he started working on stochastic bifurcations, and he also remembered from this 1991 meeting that Hasselmann explained to him that somehow he thought about the climate system as sort of Brownian motion acting on the climate systems, because the small scale, small time components act on the big, large scale climate system like Brownian motion. And that sort of also was partially certainly related to the Nobel Prize, and I found that very nice. So there is relation between mathematics and climate science already for many, many years, if you so wish. So now back to the sort of actual topic. So we want to categorize warning signs in finite dimension. So let's do this in more generality. So remember, this was the picture we had, additive noise on the fold, and we saw that indeed there was a growth in variance as we approached the fold bifurcation. So can you actually prove this? So I couldn't resist and put in a few sketches of proof. I know this is a ClimTip climate audience, but let me try to do at least a sketch of a proof for sort of, So what you would need to do this rigorously is you need to first look at the neighborhood of the critical manifold, which you can think of as this upper branch in this case. And here I've written down the formula for the upper branch. Then you write down the variational equation for the linearized process around it, which is basically you differentiate everything and you plug everything in and you linearize around this object. Then you get such an equation. And this you recognize quite quickly as an Ornstein-Uhlenbeck process. Just this Ornstein-Uhlenbeck process is modulated depending on where you are in the neighborhood of this branch. And then you define, which is quite nice, sort of the variance of this Ornstein-Uhlenbeck process, and you realize that the variance actually also satisfies a fast-slow system, but a deterministic one. Then you look at this fast-slow system, you know you need to set epsilon to 0 to somehow get the sort of slow manifold approximation for this fast flow system. So you set the epsilon equal to 0 here. You solve for the variance, and you have a slow drift of that. And then this means that for every sort of y, at least to lowest order approximation, you get that the variance behaves like sigma squared over 4 times the square root of minus v, and v approaches 0 from below. So the variance will blow up like 1 over the square root, at least on a linearized level, as you approach the saddle node bifurcation along this branch of the critical manifold. That's the formal calculation. Yeah. So what you solve, actually, the variance here, this is an example of solving a Lyapunov equation for epsilon equal to 0. I will use that later on, which is basically looking at the linearized equation and figuring out what's the variance of the linearized equation. And then you, of course, have to also estimate the nonlinear terms. You have to estimate that all the nonlinear terms do what they're supposed to do. And you can do that, and there are many different ways to do it. And here's a general result where I prove this for all sorts of bifurcations. Basically, every bifurcation up to 2 parameters, you can prove this. You can figure out in higher dimensions what's the covariance. So the covariance of the observable, of the fast variable. And you look at that these blue guys here, this DUF, this becomes degenerate. So it loses hyperbolicity at some point. And then you can figure out precisely what's the growth of the covariance as you approach a point where you lose normal hyperbolicity of the critical manifold. And you can check this for all sorts of noises, as long as the noise is sufficiently generic. This is actually true. Of course, you can make it degenerate, then it will fail. So then you look at, for example, the fold has a scaling law of v to the minus 1/2. The transcritical has a scaling law of v to the minus 1. And you can calculate, even for codimension 2 bifurcations, all the scaling laws. And the proof for this, if you do it abstractly in n dimensions for all this, works the same way, except that to solve for the covariance, you get what's called a matrix covariance Lyapunov equation, which means that the argument I have done before to compute the variance, you have to generalize. Yeah, you have to solve such a matrix equation. And there are 2 ways how you can estimate these nonlinear terms that might perturb the whole thing. Well, you can either do moment expansions and do direct integral estimates of the moments, or the methods that I prefer would be martingale methods and something called Dup's inequality that allows you to estimate that these higher order nonlinear terms by sort of an upper bound do not contribute to the leading order. They only appear in the higher order terms upon certain conditions, effectively. And this was pioneered in some sense, this martingale plus Dup, which is also known as dynamic large deviation theory, I guess. This was pioneered by Berglund and Gens in the late 90s and early 2000s. And this theory is very robust, and you can show indeed warning signs for all sorts of bifurcations. Good. Let me also highlight that this can be generalized a lot. This is more like a mathematical, some sense, generalization, but it appears in many systems, at least in ecology and in neuroscience. This is a standard sort of case. You can generalize this even to more complicated fold points. Suppose you have your normal fold, so y minus x squared, which is in the fast equation as before, so I haven't changed the fast equation at all. But suppose I make the slow equation non-autonomous by adding an extra non-autonomous term, meaning I have a z variable that I could integrate in time, meaning that there is here actually another time dependence. So I have a non-autonomous drift in the slow equation. Then you can still do this, actually. Yeah? You can still analyze it. It's just much more complicated because now you have 2 slow variables, which means that before we had a manifold that was folded and was just a parabola. Now you basically have a critical manifold that's a parabolic cylinder, because this goes 1 dimension higher, and you have a 2-dimensional flow on a parabolic cylinder. You can do that, you can analyze it, you can scale it with the blow-up method, meaning you scale everything and you look at the vicinity of the singularity. Basically, this locally removes the epsilon at the expense of pushing certain dynamics out to infinity. You can realize that this is basically 2-dimensional non-autonomous system. And then you can actually define near deterministic solution that goes towards the fold, a neighborhood, which is the definition here, a tube-shaped neighborhood around a deterministic solution that goes towards the fold. And you can ask, how much do I fluctuate around this deterministic solution as I approach the fold? Here you see some green deterministic solutions that approach the fold point that is sitting somewhere here. Basically a whole sort of, a whole parabolic cylinder of fold points is approached when you come over here. These deterministic trajectories, these green ones, are actually so-called canard trajectories. They spiral around a sort of main weak canard. And then you see in gray, there's little tubes, and these tubes are growing And in these little gray tubes, there are red trajectories, which are the trajectories from the stochastic system. And if you zoom in, you see indeed that in these sort of gray sort of bits, you indeed have red trajectories where the fluctuations grow as you approach the fold point. So these things actually get bigger and bigger the closer and closer you come to the jump point. And you can rigorously prove precisely where you are in phase space, how likely it is that you stay inside these tubes, meaning you can figure out what's the exit time from the tubes, and you can exactly quantify how big these tubes are, meaning how big would the early warning sign of the covariance be as you approach this sort of jump point in higher dimension. Meaning, if you go back to the equation, even though I've just made a non-autonomous change here and I added this in, you can still sort of, if you expand sort of triple the effort in pages in the proofs, or even quadruple the effort, so the first proof is maybe 10 pages and the other proofs here for this higher dimensional case are 50 pages, but you can do 50 pages, and after you do the 50 pages, then indeed you can show similar results to the one-dimensional case with very precise estimates where you are in phase space and how likely it is that you are close to a jump point even in higher dimensions. And you could do this for any sort of finite dimensional scale, just the effort mathematically goes up. Good. So can this be made applicable and useful? So already these finite dimensional warning signs, can this be made useful? There are many climate-based applications. I've just listed a few, a paper of Niklas, but there's also plenty others where people applied this to data sets. So people try to somehow grasp and understand all this sort of theory. Can I apply this to data sets? And people in ecology tried that too, whether it's ecology in the lab or ecology in lakes or whatever, they tried to make this useful. And also people tried this in psychology and neuroscience. And we, for example, had a very nice paper with Chris Meisel, where we actually could measure these early warning signs in actual real neurons, which we poked with electrodes. And you could even measure the right exponent. We measured in these neurons the exponent of, well, it should be a fold bifurcation in that case for that particular neuron. And we measured 0.49 for an exponent that was supposed to be 0.5. So we could even pinpoint the scaling law of the variance as we approach the jump point or the firing point in the neuron. So if you have enough data, you can do it. If you have very little data, you probably have to start arguing, which might be one of the points in climate science where it's tricky, because you don't have high resolution, high frequency data like in neuroscience sometimes, right? So that's maybe a difference from climate to neuro, if you wish. There's many further developments. You can make more complicated mechanisms that are non-bifurcation, but more global bifurcation mechanisms like saddle escapes. You can look at pattern formation and look at spatial systems and how these bifurcate and whether you can find warning signs already from the deformation of the pattern. We had a talk online, I think, of Max Riedkerk, who talked about this yesterday, I think, if I recall correctly. Yeah, so basically there the idea is the pattern is already so complicated that you see from the pattern what's going on. That's basically what the idea is. So then you can do different noises. You can look at limitations. So in certain non-Markovian systems or systems with different noise, it doesn't work, and so on and so forth. You can also look at network systems, meaning if you somehow don't want to go to the sort of full spatial resolution, but you still don't want to just do a single observable, you can basically look at multi-observables on networks, and you can look at warning signs in that context. So there's plenty of things going on in the area, and indeed this can be made useful, this finite dimensional theory. But there's sort of an elephant in the room, if you wish. So far, we have always assumed for these warning signs that we somehow only have variance of observables or covariance of observables in systems that are non-spatial. So for example, box models or simple models that are somehow at the level where you only look at a few variables. But you could now wonder if you have a spatial, multi-scale, stochastic, highly heterogeneous system, could you do it there as well? Because the AMOC, for sure, and we will come back to it, is one of these systems which definitely has a spatial aspect to it. That's clearly a spatial system where you need to look at, is there anything happening in space? So let me go through from stochastic ordinary differential equations to stochastic partial differential equations. And let me explain briefly that indeed this would work for SPDEs as well. So a little bit of background, I will be in a general domain, unknown function U. I will focus on, for now, for introductory purposes, on reaction diffusion equations. Simple reaction diffusion equation with a parameter, yeah. And this will be my playground where I will figure out if I vary this parameter V, is it actually possible that I get a warning sign for a bifurcation in the spatial reaction diffusion system, okay? Same idea, except I have to deal with this somehow more complicated spatial operator, and life is harder, yes? Life is just a lot harder. And okay, for the noise, I will again assume for simplicity for today, it's additive noise and it's a sufficiently nice space-time stochastic process, but you again could generalize this, yes? You could do that. So the stochastic process is constructed quite easily. You just take Brownian motions and then you take a spatial domain, like say L2D of some spatial domain D, and then you look at the spatial domain and you define an operator on that spatial domain and you look at its eigenfunctions. Say, for example, look at the Laplacian if you wish, yeah? This gives you a spatial resolution of the domain, and then you put the spatial resolution with the eigenfunctions qk and the beta kt's. You put them in a series, and that gives you a hopefully convergent series. In many cases, if this q is sufficiently nice, this will actually converge. This gives you a space-time stochastic process, a q-Wiener process. The derivative of this guy is at least a generalized stochastic process. Yeah? And you can show that under certain conditions, for example, if q is trace class, this indeed converges. And there's an interpretation of Q as the spatial covariance operator that tells you, okay, this is the definition. Well, so you put one in. Laplacian is maybe too complicated, so you put something bounded and nice in. So put some nice operator in, say, I don't know, just a matrix, for example. Could even be a finite dimensional matrix if you wish, then the series would be finite. Then you get a spatial covariance operator, but I will assume that the noise is white in time, but sort of colored in space. And I will assume that this trace condition is always satisfied, so everything converges. And well, it's ugly and irregular, but this is a mathematical detail that maybe for the climate audience, I will not go into much detail. So now you want to do the same thing for instability of PDEs. So you take your PDE, you assume that this is trace class, then you can write explicitly for this at least the Duhamel or variation of constants formula. And let's assume there is a trivial branch of deterministic solutions u is equal to 0 that solves the equation. And let's suppose we are wanting to analyze a deterministic bifurcation point when that occurs at v is equal to 0. That just occurs if you shift in the linear term a little bit around the spectrum, and then you get actually a destabilization of this homogeneous branch of solutions u is equal to 0. And you ask, is there still an early warning sign for the destabilization? How can I measure that early warning sign best? Huh? Okay, what you do, you linearize again. So this guy is gone. Well, it's not gone. You have to prove that it's gone, but suppose you can prove that it's gone. Then you suppose you're in the regime where you have a stable solution for the linear part, meaning this first guy in time will go to 0, which means there's only the fluctuations left where the semigroup of the linear part that defines the linear solution effectively interacts with the noise. And this is this formula here, yeah, which is basically just saying, you have fluctuations, this semigroup here, this S is sort of stable, and these fluctuations push the system around. And the closer and closer you come to the bifurcation at v is equal to 0, the weaker and weaker this pushing of the semigroup gets, and the bigger and bigger the fluctuations should become, meaning the bigger and bigger the covariance of u should become. But what is the covariance of u? Well, the covariance of u is now an operator. It's no longer a matrix, because you moved from finite to infinite dimensions by going to a PDE. So instead of a finite dimensional n cross n matrix, you have an operator. You can define this operator. It's defined via this funny looking integral, but it's basically just a generalization of the covariance operator from finite dimensions. And you know that if you let t run to infinity and there is actually a stationary solution for your covariance, it satisfies this funny looking equation here, meaning you test it with functions from your Hilbert space and you see that indeed the general covariance operator satisfies this guy. But if you paid attention in the first part of the talk, you will realize it's just the same equation that we have seen in the finite dimensional part and the first part of the talk. Yeah? Actually, this is very akin to the same equation for matrices, because here you have the linearization of the whole thing, so the A, and you have the covariance operator. So it's linearization, covariance operator, and then covariance operator, linearization. Okay, here you could take the adjoints and put everything to the other side. And then you can actually sort of, here you have the noise term that comes from the noise. And this guy, yeah, you have to solve. And once you can solve this, you can actually, oops, sorry, you can actually figure out, this was for matrices, if you can solve this here for this operator U infinity, then indeed you figure out what's the covariance operator in infinite dimensions. So you need to study the solution of this infinite dimensional Lyapunov equation, which is quite classical for SPDEs, upon varying V. You do that, and when you do that carefully, you project it, say, onto basis functions for the orthonormal basis. Suppose everything is self-adjoint, suppose my A is self-adjoint, and my orthonormal basis is sort of compatible with the basis of my Q, and everything is sort of sufficiently nice. Yeah, so you have an eigenbasis also for your A that's the same eigenbasis as for Q. If it's not, then you have to change variables or coordinates. But suppose for simplicity that it is, then you see that indeed, if you approach V is equal to 0, and if you have eigenvalues that are also close to 0, suppose for the Laplacian on a nice bounded domain, the first eigenvalue is at 0, well, then if these guys are at 0 and V tends to 0, then you see that near this bifurcation, which is either a transcritical or pitchfork bifurcation generically in infinite dimensions, the covariance operator, when projected onto the basis function, which is the crucial bit, you somehow look at the projection onto the basis functions, onto all these basis functions, if they are the suitable ones where you actually see the growth, then if you project it onto the right basis function, you see that the covariance operator blows up like 1 over V on the linearized level as V tends to 0. So this is in some sense the full generalization to infinite dimensions in a spatial temporal stochastic system of the finite dimensional warning signs. Okay, so you can also do this with continuous spectrum, and you can show that indeed for continuous spectrum, there's also a possibility that you get a blow-up, and you can even refine the continuum spectrum analysis, which we refined with my student Paolo Bernuzzi, who actually works in Critical Earth, which is yet another sort of big network that Niklas is in some sense the big boss of, partially, at least, yeah. So together with Peter from Copenhagen, and yeah, so they have run this fantastic Critical Earth network. And you see that there, Paolo figured out that you can do this also for the spectrum in infinite dimensions, and when it's continuous. And we also currently working on the case when you have slow drift, meaning if you add to this, where currently I varied the parameter statically, we are working with a lot of people trying to figure out how to do this dynamically, like in the finite dimensional case. So this is still unsolved. So stochastic PDEs with a multiscale structure is sort of unsolved. And even for PDEs, it's unknown how to really deal with this multiscale structure properly if in the V equation there's, for example, diffusion. And there's recent work, even in the PDE case, with a couple of collaborators where we are trying to prove everything. Yeah, so this is really hard stuff in the end. Good, so what about even more complicated? So clearly this is not a system that's spatially homogeneous, but it's spatially heterogeneous. So suppose you not only have a Laplacian, but also a spatial heterogeneity in a simple reaction diffusion system, then you not only get a normal operator where you know the spectrum easily like the Laplacian, but you have a Schrödinger operator. And for Schrödinger operators, you can also analyze the spectrum and figure out, you assume that this spectrum is also on the left. And indeed, you can show the following thing, that if you have a general random dynamical system for this SPDE, you can prove that it has a random dynamical system. There is actually a unique random attractor for this system. So meaning the distribution itself does not bifurcate, but you see the deterministic bifurcation when you actually approach V is equal to 0 in such cases. So there is a sort of stochastic bifurcation under suitable definitions where you see non-uniform statistics or warning signs, meaning you see growth in the variance, or you could alternatively rephrase this as non-uniform attraction rates to the steady state. And you can actually show that the two views, either the sort of trajectory viewpoint from T2 or the more abstract viewpoint by non-uniform attraction rates that was sort of proposed by Callaway in 2017, that these two fit, meaning that the sort of older theory of Berglund and Gens fits the sort of another approach in random dynamical systems theory, and all the scaling of exponents that you measure in both of these theories are consistent. So for all the climate people, don't be confused. All these mathematical theories are looking different, but in the end, they produce the same exponents, yeah, as they should. Yeah, because it's just a different way of proving things. It's not intrinsically sort of the bifurcation, that the bifurcation is the normal sort of structure that you assume. The exponents are the same exponents that you're sort of anticipating. Yeah? So that's what we proved with Paolo, even in this heterogeneous Schrödinger case. So everything is consistent. Good. So let me maybe skip this proof a little bit. Might not be that interesting. This is more for the mathematicians. You can actually show that the proof I've given via the covariance and the variance in the beginning for these bifurcations. For example, for the transcritical, we saw that the exponent should be 1. And you can actually show for a transcritical or for a general branch point that the exponent is 1 also when you do this approach of random dynamical systems theory that was pioneered by Ludwig Arnold. You take the finite time Lyapunov exponent, you look at the variational equation, you estimate the variational equation from above, and you see as p approaches the critical eigenvalue. In this case, I denoted this by lambda 1. The approach of p to this eigenvalue, which exactly means where the bifurcation is happening, has exponent 1. So also the finite time Lyapunov exponent scales with exponent 1. So it's precisely the right exponent. If you do the calculation with the saddle node, you get exponent 1/2, like it should be. So all these theories are the same, really. In the end, they give the same quantitative answer that you can use in climate science. So don't be confused. All the stuff is mathematically consistent and works the way it should. Yes. So yeah, again, you have to prove that the nonlinear terms don't matter, etc., but it's very tedious. So let me go back to the mock for like the last, do I have like 8 to 10 minutes? Is that right? Good. Okay. So let me go back to the mock. So now we made all this sort of half an hour of mathematics trying to set up that we can actually understand early warning signs for spatial, temporal, stochastic systems in a general heterogeneous setting on arbitrary dimensions. And here's a model where this is useful. This is an intermediate complexity model of the mock that I've worked on a lot with Henk Dijkstra, who is also part of all these initiatives, of TIPES and Critical Earth and ClimTip and so on. And this is a more elaborate ocean model. It's basically a Boussinesq type model where you approximate the mock and you just take a two-dimensional short or two-dimensional cut, two-dimensional cut. And in this two-dimensional cut, you basically pose this, a PDE. And this PDE actually has boundary noise. So it's more complicated. You can also do the warning signs for boundary noise. I'm not showing the mathematical result here, but we have a recent paper with Paolo and Henk where we do this. So this model, in some sense, gives you latitude, vertical coordinate, and some parameters like radius, acceleration, eddy viscosities, and some stuff that comes from convective adjustments. And it aims to model the mock in a more complex spatial temporal fashion. Yes? You also give domain and boundary conditions. So an important bit, there's stochastic freshwater forcing that we model here. This is one noise term that you actually get in. That sort of it gets put into the model, and this indeed has a wide noise term, which is zero mean. So you hope that after you did all this sort of procedure, that indeed the theorems that you have proven apply, and we have shown in a recent paper with Paolo, indeed they do. You can show for a slight variation of this model that everything works the way it should. So here's the bifurcation diagram. You indeed see this is the stream function, and this is the sum of the max and the min of the meridional stream function. And you see that there's one sort of active state of the mock. And if you go over the fold, then you go to a non-active state of the mock. So meaning that this is 0 when the AMOC has symmetric. And here there's actually an actual induced flow. And you can actually show when you approach either this bifurcation point or also this bifurcation point down here, or even this bifurcation point over here, then you can apply all the theory of spatial temporal stochastic warning signs to this more complex ocean model. Okay, and the question is, why is that? So why can you just somehow take such a theory that was developed for such a sort of easy-looking toy example, and you can apply it to really complicated stochastic PDEs that arise in climate science every day? Because we made an effort to make this theory generic, meaning that you set it up in such a way that it's not dependent upon the particular equation that you look at, but it applies to every suitably generic equation at the same time. This is the advantage of being a local theory. We are not doing anything global, because if you do global stuff, it's much harder, as Niklas already pointed out. If you look at resilience, we might have to look at more global things, which will be way harder. That's why it's sort of the new part of ClimTip and not the sort of existing part of TIPES, so to say. And if you approach this, you can actually show that the warning sign exponent here is 1/2. And if you would go down here, the warning sign exponent would be 1, because this is a branch point and this is a fold, and everything works effectively as it should. Good. So let me give you a big summary also for what we computed. We also developed stochastic numerical continuation algorithms and efficient estimates to solve all these equations, these Lyapunov equations that you need to find all these warning signs in your models efficiently, even in high dimensions numerically. So there's a whole stream of works that started probably with this paper that are written on stochastic numerical continuation in 2012, where we have proven that all these algorithms are able to actually compute the right covariance troops even in infinite dimensions with efficient and fast computers, in a sense of you can do it on a laptop machine if you wish for such an intermediate complexity model, which is very nice. And it matches precisely the scaling laws. So we tried this on several models of the intermediate complexity domain for the AMOC, and we indeed figured out that our numerical methods compute the right growth of the covariance operators in infinite dimensions. And we have extended the analytical results to include boundary noise, continuous spectra, spatial heterogeneity, and all sorts of stuff. Yeah? Good. So basically, this is now a theory that can be applied out of all these papers to your intermediate complexity or even potentially GCMs if you have an efficient computer and efficient and computational implementation available to you. Good. So hopefully I have time for a 2-minute summary. I hope that that's okay. So the 2-minute summary is, well, what we have managed is we went really from this rather innocent looking time series that we extracted from there's an observable and we want to predict what happens from that time series and whether there's a warning sign, and managed to somehow classify for all sorts of different bifurcations and finite dimensions the warning signs that could appear. And for SPDEs, we basically just started this whole development that we want to understand how patterns for stochastic PDEs can be predicted when there's a bifurcation. And I've shown you some results that at least for stationary classical bifurcations, we are already quite advanced and we have shown many things. And there are many questions still open for dynamics without normal hyperbolicity. We, of course, only have scratched the surface. And then people always come up to me and ask, well, but for this particular case, your theory doesn't apply. I was like, yeah, sure, because you can always cook up additional cases where, you can actually, you need something new. That's completely normal. There are many open questions, particularly for multi-scale finite time and stochastic PDEs that I couldn't talk about today. My apologies about that. But there are many generic applications. So not only the climate science community is now using all these papers, but ecologists and people in medicine start to use this. And does it matter? Well, I think it does, because at least the IPCC somehow started recognizing that there are these nonlinear modes, that there are these sort of nonlinear tipping points, and soon they might recognize more that there is this uncertainty quantification need for stochastic systems in their next few reports. And of course, as a mathematician, you can only make a small epsilon contribution to improve the methods that are available to all new people who look more at direct data and phenomena and who are really interested in your particular system and your particular sort of prediction. But at least I think the mathematics has put it on a much more solid footing, which I'm quite hopeful that at least that this is a useful contribution, because otherwise you would be sort of, not even being able to figure out, is this a theorem or is this something that I've just sort of guessed or computed by accident or whatever? So hopefully we are giving this whole thing a little bit of a solid footing under its main sort of big umbrella of trying to figure out whether this nonlinear climate system can do something important in the future that we need to predict or that we need to address rather quickly if it comes sooner rather than later. Good. So all of the stuff that I've talked about, you can freely download all my papers from my webpage that tries to be easy to remember from its name. And I would like to thank you very much for your attention. Thank you very much.
Thank you very much, Christian. That was very interesting. I'm sure there is questions. Feel free to just shout out. No need to raise your hands, I think. Maybe I start with one, Christian, to give people time.
Sure.
I need to think of how to formulate this as a question, actually. So yeah, so in a realistic case, we have a spatially extended system that in principle should be described by a PDE, maybe SPDE. Let's say the ocean forced by the atmosphere, maybe SPDE is a good way of approaching that. And sort of we have spatial interactions, maybe like in vegetation systems. And on the other hand, we don't have perfect timescale separation. I think all the problems in sort of our real life have these characteristics. Now, my impression is that, you know, some work, including or focusing on what you have shown, sort of extends the classical one-dimensional or low-dimensional dynamical system perspective of critical slowing down and so on to having spatially heterogeneous systems. And there's another branch of research that sort of tackles the whole non-timescale separation issues. And then you can have, on the one hand, you know, you can have rate-induced tipping, but on the other hand, then you can also have these sort of overshooting windows where you can cross the tipping point, but you don't really sort of play out the tipping because your system timescale is slow compared to the forcing timescale. Is there any attempts to bring these two directions together at some point to have something that would be realistic, you know, from a sort of climate science perspective?
Well, I mean, bringing together in some sense, it's two branches of bifurcation theory that make separate assumptions. I mean, one branch makes the assumption that you have basically a non-autonomous system where the time drift is sufficiently slow. That's an assumption that you put in. If you don't put in that assumption, then you basically say if everything's on the same time scale, you sort of leave this world of sort of modulated multi-scale bifurcations where you have a dynamic bifurcation that's slowly modulated, and you go into the world of sort of fully non-autonomous bifurcations or fully stochastic bifurcation theory. And that one is not completely solved mathematically. People work on it, but there's still open questions how you actually tackle some of the fully sort of non-timescale separated. There are still bifurcation scenarios. You can still define things the same way as I did here. The problem is many of the tools that you have here, somehow you need to upgrade quite significantly. Let me just do a simple example. It's not enough anymore to compute static spectra, but you need something like Lyapunov spectra or finite time Lyapunov exponents or dichotomy spectra. So some notion that captures a spectral notion of stability in systems that are not timescale separated. If you do that, and if you develop all these notions, I'm very confident that the theories are not really different. It's just you have a different set of mathematical assumptions, but in the end, all the tools and the results will be very much in line, meaning you still anticipate that there will be critical values where this happens, which are then the non-autonomous bifurcation points. You still anticipate if you stochastically force the system, then there could be a way that you can measure deviations that the Lyapunov spectrum is sort of slowing down or the dichotomy spectrum is slowing down, which you already see in some of the proofs that we have done. You can even see that this works the same way, the proof. And then you can hope that you can still extract potentially early warning signs for these systems. And these effects that you see, like things like, I don't know, overshoots or rate-induced tipping, there, and just in some sense, looking different if you draw them in a funny way. But if you don't draw them in a funny way, they are still normal non-autonomous bifurcation phenomena that you could analyze with this theory. Just that branch of non-autonomous analysis is not quite as advanced yet as the autonomous as well as the timescale separated one, which is natural because it's mathematically harder. Why is it harder? Because you have one more neutral direction to deal with, which is in some sense time. Yeah. So, and okay, that will take another 10, 15 years, but then I'm 100% certain that you will see these sort of whole things presented uniformly and in unison in a standard mathematical textbook. So no worries, this will get done.
Very good. Nice. Any questions from the audience? Then I give people still a little bit more time. Christian, as a follow-up question to my first one. So in principle, in the climate sciences, and like given this concern that we have abrupt transitions in some subsystem of the Earth system, and we have a situation where we don't quite believe that our models are in a position to predict sort of in the strict sense predict the dynamics of these systems under a given forcing. Even if we would know the forcing, we're not sure that the nonlinearities are sufficiently captured. There's this sort of critical slowing down is mostly then used as an alternative in a situation where we have to admit that our models are not in a position to do the prediction. We'll rather than try to go to observations and then try to identify not critical slowing down in those observations to see what, to just understand whether a given system in the real world might have approached might have been approaching a tipping point, a bifurcation point. Given what you have presented, so for example, I mean, I'm sort of, let's take my paper that you also cited. I do this extremely drastic simplification of treating the Atlantic Ocean circulation and the overturning circulation as a scalar time series by just choosing, I don't want to say purely randomly. I mean, there's something underlying it, but choosing a certain spatial region and then I average over that, and then I get a time series, and then I'm looking for CST in that one-dimensional time series. So I mean, mathematically, that doesn't quite make sense. Based on the theory that you have, is there a chance that this might guide us in sort of designing measurement strategies and sort of understanding how to measure the system if we have limited resources? We can't measure it every square centimeter of the Atlantic Ocean, also in the depth.
Yes,
So,
I mean, certainly, very certainly. I mean, the theorems tell you in some sense within which directions and which types of sort of indicator functions you need to put where on the ocean, with sort of what's the best sort of region where you could measure, at least in theory. So if you have a model, you could figure out if you put a certain measurement device in a certain region and you only measure in that region, that would be basically a projection putting an indicator function just in that region. Yeah, that would be basically what it is. And then you measure that thing, and then you are hoping that that's enough. Well, the guess would be in many cases, if it's generic enough, it is. But of course, there are degenerate cases that you could hit where it's not, as usual in mathematics. But yes, this theory gives a guidance, meaning that you can play with spatial toy models and figure out if I put my measurement device here or there, particularly if it's heterogeneous, what's the sort of best way to observe a certain type of slowing down. We have looked at this a little bit, and indeed there is progress in mathematics to figure out where these measurements could be best taken. Of course, this is not conclusive in any way, shape, or form, but this theory is active, and I would be very sort of surprised if in the next 5 to 10 years this wouldn't be a sort of reasonably finished mathematical product.
That's I wasn't aware that's already work in progress. That's very interesting.
That is work in progress, and part of it can be found in one of my papers with Paolo, but other people also worked on this a bit. So I was with high probability think that about a 10-year time span, we would be fine with this sort of spatial extraction of optimal observables for these time series.
Great. Really good to know.
As I say, we are not fast, we are mathematicians, and in some sense, maybe that's the excuse, or in some sense, we are allowed to do it, I don't know. But it just takes time to prove all these results and figure out where you can put which type of test function to figure out, are you allowed this observable, and if so, under what conditions. It just takes a lot of time to prove all that.
No worries. Be patient.
Yeah.
All right. Final call for any questions from the audience.
Well, everybody happy, that's good.
Everybody happy.
Good. Well, thanks everybody then, I guess. Thanks for listening. And if you have any more questions, I guess I'm around in ClimTip all the time. So if you really didn't understand some details, you could just mail me or ask me, that's perfectly fine.
Great. Thank you very much, Christian, also for jumping in at such short notice.
Sure.
Cool. Then everyone enjoy your afternoon. Kurt already made the announcement for our July iteration, which will be on July 2nd, I think. Likely with Imke Hopketown talking about science communication. And with that, enjoy your afternoon. Have a nice rest of the week. All the best. Bye-bye.
Bye-bye.